All right, today we're going to dive into the incredible, invisible forces that literally build our world. And we're going to start with something you definitely have in your kitchen right now, table salt. We're about to uncover the secret life of salt, and in the process, we'll get a handle on one of the most fundamental ideas in all of chemistry.
I mean, have you ever really thought about it? You look at a grain of salt, and it's just this tiny, perfect crystal. But what's the invisible glue holding it all together so tightly? Well, that's the big mystery we're solving today. And believe me, it's a story of atomic drama.
So to understand salt, or sodium chloride to be technical, we've got to meet our two main characters. We've got a sodium atom, and we have a chlorine atom. Now, like pretty much all atoms, they have one big goal in life. They just want to be stable. And they are willing to do something pretty drastic to get there.
Okay, so what's so interesting here is that these two atoms are a perfect match because they have completely opposite problems. You see, sodium, which is a metal, has this one lonely electron in its outer shell. It is desperate to get rid of it. Meanwhile, chlorine, a nonmetal, has 7 electrons out there, and it just needs one more to feel complete. One is dying to give an electron away, the other desperately needs to take one. See where this is going?
And that right there, that sets the stage for the main event. We're about to see a transaction that's going to fundamentally change both of our characters forever. And this isn't some polite sharing agreement. No, this is a full-on transfer. But wait, before we see the giveaway, we need one key piece of vocabulary. You see, when an atom loses or gains an electron, it's not neutral anymore. It becomes something called an ion, which is just an atom with an electrical charge. This idea is absolutely central to what's about to happen. And boom, here's how it goes down. Sodium just gives its one outer electron over to chlorine. It's a clean handoff. Instantly, sodium, because it lost a negative particle, becomes a positively charged ion. We call that a cation. And chlorine, having gained that electron, becomes a negatively charged ion, or an anion. So why? Why all this drama? Well, the goal for both of them is to get that perfect, super stable electron setup, the exact same one that the ultra-chill noble gases, like neon and argon, have. By losing that one electron, sodium's new outer shell is perfectly full, and by gaining one, chlorine's outer shell is now full. Everybody wins. So just look at this transformation. The sodium atom goes from being neutral and unstable to being totally stable, but now it has a permanent positive charge. It got what it wanted, but it's changed. And of course, the exact same thing, just in reverse, happened to chlorine. It's now a stable but negative ion. So now we have these two brand new ions. One is positive, one is negative. And as anyone who's played with magnets knows, opposites attract. But we're not talking about a tiny little spark here. This attraction is an incredibly powerful force. And this right here is the whole point. That force of attraction is the ionic bond. It's not a physical string or anything. It's an invisible but super strong electrostatic force that just glues these oppositely charged ions together. This is the very foundation of what makes salt, salt. And you know, there's a really simple, almost elegant logic to how we name these new compounds. You just say the name of the metal first, in our case, sodium, and then you take the name of the nonmetal, but you change its ending to "ide." So chlorine becomes chloride. Put them together, you get sodium chloride. And it works the same way for all the others you see here. Simple, right? But here's the thing. An ionic bond is almost never just a one-on-one deal. A single tiny grain of salt has trillions upon trillions of these ions. So how do they all arrange themselves? Well, they build something much, much bigger. Yeah, they don't just form some messy clump. Nope. They build a highly organized three-dimensional structure called an ionic lattice. The best way to think about it is like a perfect, repeating checkerboard of positive and negative ions stretching out in every direction. So inside this crystal fortress, every positive sodium ion is completely surrounded by negative chloride ions, and every negative ion is totally surrounded by positive ones. Those powerful electrostatic forces are pulling in every direction at once, locking all the ions into this fixed, super rigid structure. And what's really cool is that even though it's made of charged particles, the whole crystal has no charge at all, because all the positives and negatives perfectly cancel each other out. Okay, now for the best part. This microscopic structure, this invisible fortress we've been talking about, is directly responsible for the real-world properties of salt that we can actually see and test. It gives ionic compounds some pretty unique powers. Power number one, a ridiculously high melting point. Those electrostatic forces holding that lattice together are just so strong that it takes a massive amount of energy, a ton of heat, to break them and let the ions move around. The melting point of salt is over 800 degrees Celsius. That's why you can have a screaming hot pan on the stove and the salt just sits there, completely unfazed.
Now, here's a weird one. Ionic crystals are incredibly hard, but at the same time they're brittle. Why is that? Well, if you hit a crystal with enough force, you can actually shift the layers of the lattice just a little bit, knocking them out of alignment. All of a sudden, you've got positive ions lined up right next to other positive ions, and negatives next to negatives. The repulsion between those like charges is so immense that it literally pushes the layers apart, and the whole crystal just shatters.
Okay, what about conducting electricity? Well, the answer is, it depends. When salt is a solid, all those ions are locked up tight in the lattice. They can't move, so solid salt cannot conduct electricity. But if you melt it or dissolve it in water, you free the ions from that rigid structure. Now you have mobile, charged particles that can move around and carry an electrical current.
And finally, why does salt seem to just disappear in water? Well, water molecules are a little bit special. They're polar. That means they have a slightly positive end and a slightly negative end. These polar water molecules are really attracted to the ions in the salt crystal. They swarm around them, and that attraction is strong enough to literally pull the positive and negative ions right out of their fortress, letting them float freely in the water.
So, to wrap it all up, this table really tells the whole story. You've got your giant ionic structures, like salt, made of ions. They have high melting points, and they only conduct electricity when those ions are free to move. And that's a world away from simple covalent substances, which are made of small, neutral molecules. They tend to have low melting points, and they just don't conduct electricity at all. The structure, deep down at the atomic level, determines everything.
And that is the secret life of salt. It's a whole story of atomic give and take that builds this powerful invisible fortress. So the next time you see any kind of crystal, whether it's salt, a gemstone, or even frost on a window, you can stop and ask yourself, hey, I wonder if this is another story of ionic bonding at work?